Okay, so I think today I want to move into, I barely previewed triple integrals, and that kind of starts here in 14.6. And I want to get into them, so I just want to start by doing a problem. So there's this problem 16, I might do a couple problems. So there's this problem 16 that says, the directions up above say, set up the integration, the triple integral, to get the volume of this solid. The solid is bounded above by the cylinder, z equals 4 minus x squared. They just referred to this as a cylinder, and they just said that the solid is bounded above by this. So it's bounded, the solid is bounded above by this, and bounded below by the paraboloid, z equals x squared plus 3y squared. I'm going to write the phrase like they said, bounded below by z equals x squared plus 3y squared. Okay, so they refer to this as a paraboloid. You know, I feel like I'm working in 3D here, that I need to set up a triple integral to get the volume of this solid. You know, in my preview the other day, when you're doing a triple integral to get volume, what function do you integrate? Do you remember what I might have said? No. Okay, a 1. I mean, there is, the quick analogy here, one more time quickly, was when this chapter opened, we would integrate over a region R, and when there was kind of no function there, or just a 1 there, we called that area. Well, to tell you the truth, the book called it the area of region R. I said, the book was lying to you. It's really the volume of something with a height of 1. That's z equals 1 right there. But of course, the volume of something with a height of 1 is numerically equivalent to its area. So your book is calling this area. That's okay, we can go with that. And then we said if we're doing a double integral and we put a function in there, well then it's volume. I mean, then it's the volume between the region in the xy plane and the surface up above, and there's a solid created by the surface and the region in the xy plane. And so now it's the volume. And then I moved up. The analogy is, here we go. We integrate a triple integral over the volume of a solid S, not a region R, but a solid S. And anyway, the analogy kind of comes from up there. A triple integral, when you're integrating a 1, we're going to call volume. Although maybe it's actually some higher dimension than volume. Never mind. And then I can do some triple integrals with a function in here. But this is a 4th dimensional function. I can integrate with respect to the volume of the solid. I can integrate some 4-dimensional function over a 3-dimensional solid S. And I kind of made a joke. I don't have a geometric meaning for this. And so I said, only God knows what this is. And God's okay with making a few jokes every once in a while. So, geometrically speaking, I don't have anything for this. But it is kind of a joke. Physically speaking, if this is a density function and you integrate over the volume of a solid, the density integrated over that volume, we might end up with the mass of that solid. So there are physical meanings for these triple integrals. It's a joke when I say we don't know what it means or we don't know what it does. But geometrically speaking, it's not a joke. Geometrically speaking, I'm up a dimension from volume, and I got nothing for you there. I'm up 1 dimension from volume, and I got no word for that. Anyway, we're asked to do volume with a triple integral. My point is, I don't need anything here. All I need now is my dv. I need a 1 here, and I need my dv. Now the problem with triple integrals is the dv comes in 6 possible forms. dz, dy, dx, dz, dx, dy, dy, dx, dz, dy, dz, dx, dx, dy, dz, dx, dz, dy. There's 6 possible orders of integration. So, what a pain. You know, which one should I do? Well, it's kind of obvious. I mean, and it's we've been working with x's and y's, and we've got the z right here. I mean, what we'd like to do is take care of z first. I mean, that's kind of the way we think. But in reality, all these variables are just variables, and it doesn't matter. But if we let z go first, then we got z going from a lower surface maybe to an upper surface. Or maybe the lower surface is 0 to some upper surface. But in this case, the way they describe this, I have some solid that's bounded above by this and bounded below by this. So without a whole lot of drawing or thinking, I think my z would go from a lower bound of this z to an upper bound of this z. Now, I think that was easy. Sketching this would be tricky. I might need to sketch it, but the way this was worded, it sure was nice. They told me who was on top and who was on bottom. So I'm integrating from the bottom z to the top z between these two surfaces. But maybe to set that up, I really need a 3D picture. But the truth is now, to finish this problem, I can either do dy dx or dx dy. And in order to figure that out, I might need a 2D picture of, I don't need the 3D picture. I've sort of taken care of the z aspect of this triple integral. But to set up the rest of this, dy dx or dx dy, maybe I need a 2D picture of the region over which I'm integrating. Well, to get the 2D picture, I feel like I need a 3D picture. What is going on here? What is going on here? You know, when they wrote the word, they wrote this word, I didn't write it. They called it a cylinder. You know, what they mean by that is they call a cylindrical surface because it's got this missing variable y. You know, what he really is here is he's a parabola, not a paraboloid. They call this a paraboloid. This is a parabola. I think it hits here at 4. I think it hits the x-axis at 2. And because y is missing, it's this parabola. And by the way, it's on the back side of this too, over here on the negative x-axis at -2. It's this parabola that runs out the y-axis, infinitely out here in the direction of the y-axis. Kind of just an upside down parabola sheet. Z equals 4 minus x squared. By the way, infinitely off in this direction too. Oops. Anyway, what was that? That was all just to draw one surface. Below that is a paraboloid that opens up from the origin. You know, these paraboloids just kind of open up like this. Some of them are very circular. They look like this. But this one happens to be elliptical. So I hardly draw it any different, but it's elliptical. What's it doing? It's coming up. Geez, it hits. You know, on its way up, it's hitting this parabola that's coming down. Gee, wow. Yeah. It starts to get messy. This is tough. Drawing these 3D images is tough. I mean, up until triple integration, we kind of got away with just sketching the region in the 2D region over which we were integrating. I didn't necessarily always need a 3D picture. Some of these 3D pictures are tough. I'm having a hard time. I mean, what's not hard is I got an upper surface and a lower surface. But what exactly does this object look like is tough.
I think it's a saddle-ish.
That's not a bad idea, saddle-ish, right. It's got this top though, it's got this top.
True.
But then it's got this funny, I think where they intersect is saddle-ish. I like that. See where they might intersect. Let me get rid of some. And that's what I am trying to come across, where they intersect. Because I've got a top surface, I've got a bottom surface, but their widest point at which they intersect turns out to sort of be the region over which I'm integrating. Let's just, I'll tell you what, how do we find where two things intersect? I mean, again, I'm having a hell of a time drawing it, but forget drawing it maybe. Where do two things intersect? How do you proceed when two things intersect? Yeah, there's a Z, there's a Z. Let's set them equal to each other. Let's set them equal to each other. Okay, if I add this x squared over here, then I get 2x squared plus 3y squared equals 4. Well, I know what that is. You know what that is?
Looks like a circle.
Well, it does look like a circle, but when the coefficients are different, it's an ellipse. But that was a good idea. Right, it's a circle, but not an ellipse. Yeah, good. So they intersect in some elliptical region here. Well, so to determine the rest of these bounds, dy dx, I kind of had to do this work. This is where they intersect. They intersect in this xy curve here. Now, you know, this is again, this is not in the xy plane. I mean, the region in the xy plane is a dot. I mean, there is no region in the xy plane. But this intersection place is somewhere here. There's a top surface, there's a lower surface, and this is where they intersect. And it's this elliptical intersection region. The shadow of this is the region over which I'm integrating. So the shadow of this, I can pretend this is in the xy plane, and this is what I'm integrating. All right, so I can pretend I'm in the xy plane, and I can pretend I got this ellipse, and the name of this ellipse is 2x squared plus 3y squared equals 4. If I've set myself up for y to go next, what do you think your y bounds would be? Well, I think it would be this lower part of the ellipse to this upper part of the ellipse. So I would solve this ellipse for y. This is getting nasty. Solving this for y would be 3y squared equals 4 minus 2x squared. Divide by 3, take the square root. Y equals plus or minus the square root of 4 minus 2x squared all over 3. Wow. And I think my bounds for y are the semi-ellipse, or the under part of this ellipse, the lower part of this ellipse, which is the negative square root, to the positive part of this ellipse, which is the positive square root. So that's what I need as my bounds for y. The negative square root of 4 minus 2x squared over 3 to the positive square root of 4 minus 2x squared over 3. For the bounds for x now, please, finally, the bounds for x are just the extreme left x to the extreme right x. What would that be? Boy, oh boy, I guess I need some more details about this ellipse. I can find those x-intercepts, though, if I pretend y is 0. If y is 0, I get 2x squared equals 4. I can divide by 2, and divide by 2, x squared is 2. So I think I just found these places. Plus and minus the square root of 2. When y is 0, x is plus and minus the square root of 2. And I think that would be the extreme left and right of this ellipse. So there's my bounds. Hey, I'm very happy this was problem 16, and I did what they asked. They said, set up a triple integral to get the volume. So we did. They do not want me to do this integral, and I do not want to do this integral. Look at those bounds. This is not, I mean, you could integrate the z pretty easily, and you could, but then from then on, you're integrating this no, I don't want to finish this problem. I don't have to. But we can set these up, and I think it was sort of a tricky enough setup. Sort of. I'm sorry. I don't know how. I mean, it started off easy. I had a lower z and an upper z, no problem. Or vice versa. A lower z and an upper z, no problem. But to analyze the XY region took a little bit of work. I had to look for the intersection. I had to think about this elliptical region. It's really not in the XY plane, but pretend it is in the XY plane. You get your lower Y, your upper Y, your left Z, your left X, your right X, and you finish setting up your bounds, and that's the answer for the volume of whatever this is, whatever that is. Yes?
Well, I mean, isn't it, I mean, almost literally, I mean, kind of and kind of not, but, I mean, in Cal 1, and to some extent Cal 2, but it's kind of the domain of both, we had, you'd have a line, and you'd find the area underneath that line to, well, y equals 0 at first, and then you had another line, and you'd find the area between those two by subtracting. And what you're doing really, I mean, it seems to me, is taking a double integral and then subtracting, and then taking the upper bound and subtracting by the lower bound.
Well, you're right, and you're right. One of the things in my notes is, now they forced me to do this with a triple integral, so we did. And one of the things that my notes don't really talk about volume between two surfaces. But the other day we ran into a problem. Let me just, so you're on to something, just to answer your question. The other day we ran into a problem that before I learned about triple integrals, they wanted me to do a problem kind of like this. There was an upper surface and a lower surface, but they wanted me to do it with a double integral. So how would that change? The function you're integrating, instead of just being a function, it would be, if you have an upper z and a lower z, you would subtract the two z's, right? So you're exactly right. So there was upper surface minus lower surface. So it would be this minus this, and then set up the bounds dy, dx. So you're right. And by the way, integrate this one time, you'll get a z, you'll plug in your bounds, and you'll be here. So one iteration of this triple integral lands you right here. You were sort of suggesting that you could have set up this volume with a double integral, and you can. Upper surface minus lower surface, you're exactly right. They asked for a triple, so we did it. Let's do another problem. Go ahead.
Well, I mean, I take it the importance of the triple integral, I mean, therefore, isn't so much with volume, specifically volume of solids, but the
other thing, maybe.
Yeah.
Yeah, you're right. And also, we're going to see some more yeah, we'll see some more stuff here. But you're right. In rectangular coordinates, dz, dys, dx's, dy, these aren't far from each other. You're right. These are pretty darn close. One iteration of this lands you here in a lot of ways. Right. Right. Here's one of the challenging problems is this 30. I'm going to do this 36, and I don't know how much of this I'm going to do. But in 36 and in 14.6, they give me this picture. Right. They give me this picture. This is a good 3D picture. This is my x-axis, my z-axis, my y-axis. This is 9. Comes down here, it hits at 3, and the name of that surface is z equals 9 minus x squared. Very similar to what I just did. Z equals 9 minus x squared is the name of this surface. Y is missing, so this parabola extends out into the y direction, but hold on. They do this thing, they cut it off right here with this plane y equals x. Got this line here, y, this is good old y equals x, which is a diagonal plane coming through here. They've got this touching here, so this is 3, this is 3, 3, and then this arcs down like this to this corner. Yeah, Yeah, so this y equals x is sort of, or this plane here, y equals x. And this line here. So, that's a funny shape. It's got this curved parabolic front, kind of, or top here, over this triangular region. What they did was they already set up a triple integral for me. They have this all set up for me. They have a triple integral set up for this volume. They call it dz dy dx. There's a 1 right here, and then they do it dz dy dx. And for dz dy dx, they have 0 to 9 minus x squared, 0 to x, and 0 to 3. They have this all set up for me here. Might be kind of fun just to double check, are they right? If I look at this picture and let z go first, I think z would go from z equals 0 to, boom, this surface. This surface is coming down at me here. Boy, the picture gets cluttered. To this ceiling, this thing's my ceiling. So from 0 to the ceiling, from the floor to the ceiling. After that's done, you really can, in order to figure out the other bounds, you can look at the 2D region over which you're integrating. Another way to say that is the shadow that this solid casts into the XY plane. I can see it right there, but if I blow it up a little, it looks like this. It's y equals x is this line, and it's bordering the x-axis at 3. Don't get the wrong axis there. So now, what would be the bounds for dy and dx? Well, I guess they say dy goes from 0 to x, or y goes from 0 to x. That makes sense. And then x goes from 0 to 3. That takes care of it. Z goes from the floor to the ceiling, and then we let y and x range through this region. Cool. So they gave me all that. And what they want me to do, their directions say, now set this triple integral up with the other 5 orders of integration. And so that might not be too bad here on 36. I do have a cluttered picture there. Let's see. I'll tell you the easiest one. The easiest one would be dz dx dy. Since we already have dz dy dx, it's easy to go to dz dx dy. I think the z would do the same thing. 0 to 9 minus x squared. But the x's and the y's now have been switched. So when I look at this region in the xy plane, I have to let x go first and y go second. If I let x go first, can you tell me the bounds for x? If x is going first,
You get 0 to 1.
no. If x goes first, it goes from left to right, and so it goes here. There's x moving. So that means x is going from this x, which is called y, over to this x,
3.
which is called 3. So I think it goes from y to 3. From y to 3. While y goes from, now y's last, while y goes from 0 to 3. So that wasn't hard, but it was just a matter of rethinking this region to finish x and y. Let's try another one. Let's try, I don't know, let me try dx, dy, dz. By the way, I want to do this in order. I don't really like doing these problems I mean, I want to do it in the order, I guess. But sometimes it's fun to look at the z. If the z is last, the z is last now. And the last guy is always just plain old numbers. You know, it's typical for these first bounds for z to be in terms of the remaining variables. So the first bounds are in terms of the x's and y's. Once you've taken care of him, then the next bounds are in terms of, well, for this one, the bounds for x are in terms of the variable that's still coming, y. And then the last bounds are numbers. Anyway, so I was thinking about the bounds for z, which is last. What do you think those numbers will be?
0 to 9.
Sure, 0 to 9. I could fill that in, but that's z going last. Who's going first? X. Okay, X is going first. Okay, what does that mean? So instead of floor to ceiling, that's kind of X is, here's X. The X-axis, that's like back to front. So that's coming from the back to the front. Wow, I can see it. It's kind of tricky. But I think the back wall is this slanted wall. I think that's the back wall. I think any X you arbitrarily put in this solid and have it come out toward you, I think it starts on this back wall and then it comes out and hits this curvy front wall. So I'm going to just call that the back and that the front. And now here I am. I want to go from that back X, which I'm calling Y, to my front X, which I better call Z minus 9, 9 minus Z, square root. X is the plus and minus, but I think this one's the positive square root of 9 minus Z. Yeah, good. That's this thing solved for X in terms of Z, which is what I need. I think we just figured it out. My X goes from that back X, called Y, to this front X, called the square root of 9 minus Z. Hey, after you've taken care of X, like I did up here, after I thought about Z, I could look at the 2D region in the XY plane. To finish the bounds, I could look at the 2D region in the XY plane. And watch this. This is important. Now that I've taken care of X, I can look at the 2D region in the YZ plane, which is different than this region. What does the 2D region look like in the YZ plane? Ooh, actually, if I look back on that YZ plane, there's nothing there. Okay, well then it's the shadow of this thing in the YZ plane. And I think it would be this. Will that be the shadow back there? I think so. This wall, this sort of curvy wall would throw that shadow on there. Wow. I already filled in that Z was going to go from 0 to 9. I wonder what Y is going to do. I guess Y has to go from 0 to this thing. What the hell's the name of this thing?
I don't think it's 9 minus x squared.
Well, right, it was called 9 minus x squared. It was Z equals 9 minus x squared. Now, hold on. But x is already done. Remember, we took care of x. So if I'm going to start, I need to talk about y's and z's. I'm in the yz plane. I don't need x.
Well, y does equal z.
But y does equal x. Thank you.
Yeah, right.
Y does equal x. So I could replace that x with, you're right, z equals 9 minus y squared. That's what this is. And it hits the y-axis at 3. Yeah, that's what this is. Wow. All right, so what am I trying to do? I'm trying to analyze this region just so I can get my bounds for y and z. Which, by the way, I've already done z, 0 to 9. So I need my bounds for y, which I think would be 0 to
9 minus y squared.
Well, yeah, except, hang on. You don't put, yes, it's 0 to 9 minus y squared, but I have to name it y equals some function of z. I need y equals some function of z. If I solve for y in terms of z, it'll be the square root of 9 minus z, I think. Yeah. That's what I need. I need this y equals 0 to this y equals this. again, one more, we're done. But when you integrate x, its bounds are in terms of the variables to come, y's and z's. When you integrate y, its bounds are in terms of the variables to come, maybe numbers and z's. When you finally get to z, there should just be numbers there. I mean, that helps me, anyway, organize how to solve these equations for which variables. Just knowing that you've already integrated x, there should be no x's in these bounds. There should be no x's in any bound in this problem. It's a little tricky, man. Rewriting the equation, solving for y, solving for z, I mean, I think this is a little tricky. Switching the order of integration are challenging problems. I didn't assign too many, but it helps your brain think. I think it helps you think through these 3D things: left, right, front, back, or back, front, left, right, bottom, top. I mean, that's how we got to think about these x's, y's, and z's. Yes?
So, and I think you mentioned when I was talking about, doing the triple integral and essentially doing a triple integral using a double integral.
Right.
You mentioned that would work in rectangular coordinates.
Right.
So, for example, would these bounds be improved if you turn them into rectangular coordinates?
Well, they are.
And how exactly would you do that with the third variable?
All right, hang on. We're in rectangular coordinates.
Oh, I meant, sorry, polar coordinates.
Well, with these triangular regions and parabolic stuff, polar coordinates aren't cool. What we learned in 14.3 was when you integrate over these circular regions, polar coordinates are sure helpful.
What about ellipses?
Yeah, ellipses aren't cool in any coordinate system, really. Yeah, they're they can be nasty, right? Polar might be better, maybe, but they're tough. So anyway, this is enough. This is enough of 14.6. I got some other stuff I want to say. So I'm gonna. I mean, there's more to this problem. They want me to do this for for other orders of integration. Same problem. They want me to do it for all 6. They gave me one, and they want me to do it for the other 5 orders of integration. And maybe you guys could finish that one. I really want to totally switch gears and talk about other coordinate systems. So this is where see, what's next is 14.7. And 14.7 is triple integrals in spherical coordinates and cylindrical coordinates. Okay? Well, guess what? You guys don't know what these are. Okay? I need to stop and tell you what these are. So that takes me back to 11.7. I skipped these at the time because we had no use for them, but now we need them. So let's go back to 11.7 and learn about this brand new coordinate system, these brand new coordinate systems. So in 3D, these are brand new 3D coordinate systems. So check this out. When you're in 3D, you have this x-axis, y-axis, and z-axis, and this first octant here. You come out a distance x, you move over a distance y, you go up a certain distance z, and that lands you at a point called x, y, z, an ordered triplet, so to speak. But there's another way to get there. Cylindrical coordinates can get you there. Cylindrical, by the way, these are rectangular coordinates, okay? Good old x, y, and z are rectangular coordinates. And we're all real familiar with those. We might not even call them rectangular coordinates because we never had other coordinate systems, hardly ever.